It seems effortless. A simple turn of a faucet, and clean, fresh water flows into our homes. This convenience, this constant availability of potable water, is one of the defining hallmarks of modern urban life.
Yet beneath this tranquil domestic scene lies an immense engineering challenge. How do we reliably deliver billions of gallons of drinking water to sprawling metropolises?
Often, the sources are far away, sometimes at lower elevations than the neighborhoods they serve. The fundamental paradox is clear. How does a city defy gravity?
It requires not just pipes and pumps, but a mastery of physics, hydraulics, and sheer logistical scale. We are talking about moving massive volumes of liquid uphill, consistently, efficiently, and without fail.
This is the invisible circulatory system that keeps civilization running. Engineers must overcome this challenge using gravity feed systems, massive pumping stations, and sophisticated.
The journey begins far upstream, at the point where nature provides the raw material. These vast catchment areas, these sprawling reservoirs or deep-rooted aquifers, are humanity's initial holding tanks.
Here, water is collected from a massive basin, often dammed back into its natural river course to create stable storage. Before any major infrastructure can draw upon it, however, preliminary processing must occur.
The raw intake point requires screening and initial filtration to remove large debris, sediment, and organic matter.
This critical first stage acts as the gatekeeper, ensuring that what enters the engineered system is manageable enough for the complex journey ahead. It is where nature meets the necessity of control.
From these controlled sources, gravity is our first ally. The water moves through massive conveyance tunnels and open canals, harnessing natural gradients to begin its steady descent toward urban centers.
While gravity provides a powerful initial push, cities rarely operate on pure natural gradient alone. To reach the highest points of modern metropolitan sprawl, we must actively fight the pull of Earth with technology.
This is where the force multipliers come into play. Massive pumping stations and booster facilities.
These aren't merely pumps. They are sophisticated hydraulic engines that generate immense pressure, or hydraulic head, to lift water over hills and maintain flow across vast distances.
By strategically placing these booster stations, engineers create a network of controlled pressure zones, ensuring that the delivered volume remains consistent, regardless of topography or demand fluctuations.
It is an intricate dance between civil engineering might and fluid dynamics. These stations utilize powerful electric motors to overcome friction losses and elevation changes.
They maintain critical pressure zones, the hydraulic backbone allowing water to reach every faucet from the highest skyscraper to the furthest suburban tap.
Beneath our feet lies a vast, silent circulatory system, a labyrinth of pipes that dictates the rhythm of urban life.
These mains and feeders are not merely tubes. They form an intricate network designed to manage pressure across wildly varying topography.
Engineers must account for everything from sudden demand spikes in dense downtown cores to the gradual drawdown in outlying neighborhoods. The challenge is maintaining consistent, reliable pressure everywhere.
This requires sophisticated hydraulic modeling and strategic zoning.
By dividing the city into distinct pressure management zones, utilities can isolate areas and fine-tune flow dynamics, preventing overpressurization that could damage older infrastructure or underpressurization that would simply cut off service. It is a continuous act of balancing physics with metropolitan growth. These zones utilize specialized valves and pumps to regulate force precisely. This hydraulic ballet ensures that whether you're on a hilltop—
But even when the water reaches its destination, or rather, as it nears the point of consumption, the journey is far from over.
Moving the volume uphill is only half the challenge. Ensuring its purity requires an equally sophisticated process. At the treatment plant, raw source water undergoes a rigorous chemical and physical transformation.
First, chemicals are introduced to encourage particles, from silt to microscopic pathogens, to clump together in a process called coagulation.
These larger clusters or flocks are then settled out, followed by filtration through layers of sand or advanced membranes. Finally, disinfection, often using chlorine or ultraviolet light, neutralizes any remaining biological threats.
This entire chain of purification is not merely an additive step. It is the critical safeguard that makes municipal water safe for our most basic needs.
The physical journey through pipes and tanks is only half the story. Guiding this immense flow, however, is a sophisticated digital layer, the modern control system.
These are supervisory control and data acquisition, or SCADA systems. At their core, SCADA allows utilities to monitor every pump, valve, and reservoir in real time from a central command center.
They gather data on pressure levels, chemical concentrations, and flow rates across vast networks. This constant stream of information is the nervous system of modern water delivery.
It enables operators not only to detect failures, like a sudden drop in pressure indicating a leak miles away, but also to remotely adjust operations.
By optimizing pump speeds or redirecting flows through automated valves, SCADA ensures that potable water reaches its destination efficiently and reliably, adapting instantly to changing demand patterns across the city.
But even the most sophisticated system is not immune to failure. A catastrophic pipe burst, a major pump malfunction, or an unexpected contamination event can bring operations to a grinding halt.
When the primary arteries of water delivery fail, the immediate challenge shifts from optimization to sheer survival.
Modern utilities must therefore plan for redundancy, the concept of having backup pumps, alternative feeder lines, and emergency isolation valves ready to activate instantly.
This resilience is increasingly dependent on advanced leak detection technologies, which can pinpoint minuscule leaks or structural weaknesses long before they escalate into service-disrupting emergencies.
It's a constant race against entropy, requiring both robust physical infrastructure and preemptive digital intelligence. These protocols are rigorously tested through simulated crises, from full-scale grid shutdowns to localized contamination drills.
Such preparedness ensures that even when failure strikes, the critical function of delivering clean water remains uninterrupted.
But this resilience is increasingly challenged by factors far beyond aging pipes and outdated pumps. Growing populations intensify demand, while climate change introduces radical instability to traditional sources.
Prolonged droughts strain reservoirs, and extreme weather events accelerate contamination risks, forcing utilities into a state of perpetual crisis management.
To secure the water supply for future generations, innovation must pivot from mere maintenance to fundamental reinvention.
This means embracing advanced recycling technologies, treating wastewater not as waste, but as a reliable resource sometimes called toilet-to-tap reuse.
Furthermore, integrating smart grid capabilities allows systems to predict localized failures and dynamically reroute flow, maximizing efficiency under duress.
The future of urban water supply is less about building bigger pipes and more about becoming an intelligent, circular system itself. These integrated approaches, from decentralized purification units to AI-driven leak detection, are redefining urban resilience.
They shift us from the distant mountain source, through miles of subterranean piping, to the final tap in a skyscraper. The journey water takes is an epic feat of civil engineering.
It is a complex, often invisible lifeline that supports everything we consider modern life: sanitation, industry, health, and commerce.
This intricate web of pipes, pumps, and treatment facilities doesn't just deliver gallons. It delivers the fundamental prerequisite for urban existence itself. The reliability of this system dictates the rhythm of our cities. It is a testament to humanity's capacity to manage resources at an immense scale, ensuring that even as populations grow and climate pressures mount, the essential flow remains uninterrupted.
This unseen infrastructure is the silent engine powering the modern metropolis. From gravity-fed aqueducts to advanced pumping stations, this constant vigilance ensures that clean water reaches every corner.
It is a monumental commitment, a silent promise underpinning the very pulse of civilization.